Hello.
Yes, sir, you are audible. You are just starting our webinar within 2 minutes.
Okay, my voice is audible, huh?
Yes, sir. Yes, sir. Your voice is
Okay,
audible.
okay.
So, good afternoon, all the faculty members, research scholars, and students. Wishing you a heartiest thanks for your presence in today's session. I, Dr. Nirmala Mollik, on behalf of the Department of Electrical Engineering, Dumka Engineering College, welcome you all in day 2 in this 3-day online seminar. At first, I would like to thank the respected authorities of Techno India Group and my colleagues in Dumka Engineering College for their dedication to helping us to arrange this seminar. Now, I would like to welcome our session chairperson for day 2, Dr. Rohit Babu, Associate Professor, Lendi Institute of Engineering and Technology, Vijayanagram. Sir, we are very much thankful to you for giving your precious time to be here with us from your busy schedule. Let's take a glimpse of the journey of Dr. Rohit Babu, sir. Dr. Rohit Babu received his BTech degree from United College of Engineering and Research, Greater Noida in 2011, and MTech degree from Indian Institute of Technology, BHU, Varanasi in 2013. He obtained his PhD in Electrical Engineering from the Department of Electrical Engineering, IIT Dhanbad in 2020. Presently, he is working as an associate professor in Electrical and Electronics Engineering Department, Lendi Institute of Engineering and Technology, Vijayanagram, India. Previously, he also served the Department of Electrical and Electronics Engineering of Raffles University, Rajasthan, and Bharat Institute of Engineering and Technology, Hyderabad, as an assistant professor. His research interests include power system observability, optimal PMU placement, state estimation, evolutionary approaches, power system optimization, reactive power planning, economic load dispatch, and FABS devices. So thanks to all for keeping this patience. Now it is being informed to all the participants that a link for the attendance will be shared anytime in between the session. Now I would like to hand over the session to Dr. Rohit Babu sir. Rohit Babu sir, over to you.
Okay, thank you, Dr. Malik. And thank you for giving me the opportunity. I think my voice is audible. Okay.
Yes, sir, you are audible.
Okay, thank you. So now let's start the session. So today's topic is allocation of Phasor measurement unit in smart grid. So now, first of all, let's understand this topic. What is the meaning? So in this, the allocation means that we are talking about the optimal or strategic position of phasor measurement unit as because of the cost. So it is unwise to install phasor measurement unit on your system on network. So we can't take a chance. And also in smart grid, so as you know, the term smart grid, this term is coined in it is around 2007. Okay, and this term itself says the grid which work smartly. So we can say that if it's a smart grid or smart network or smart city. Nowadays you are listening so many words on this smart. So smart means what? A system which works smartly. and how the system will work smartly by adding some extra things. Like suppose if we talk about the power network, so we are using for monitoring, we are using phasor measurement unit, and for improving of your reactive power compensation, so we are using FEC devices. And for voltage problem, and suppose if there is a voltage imbalance, so now we have other devices, that is DVR. So all these things makes a grid smart, and all these devices makes a grid smartly work. Now wait. So okay, and I think this is not required. Okay, now the today's sessions, its content is, first of all we'll talk about the introduction, and followed by the problem formulation and observability analysis based on phasor measurement unit, and then again same problem, that is optimal placement of PMU problem, we will solve with the use of binary particle swarm optimization technique, and if time permits, I will show you the codes also, that how it work. And the third point is that as we know that like there is a constraint in power network. So here we have considered weak bus constraint. So what will happen whenever we are considering weak bus constraint in power network, and how this PMU will behave, and like how we can place PMU after considering the weak bus. So we'll discuss. And the fourth point is based on the complete and incomplete observability. So it is also based on the depth of unobservability 1 and 2. So also we will talk. And again, the second method is placement of PMU using two-stage branch and bound algorithm. So again, we will talk about the two-stage branch and bound, and how we can use this two-stage branch and bound in case of optimal placement of PMU problems. Now let's talk about first of all the phasor measurement unit. So phasor measurement unit, it is a device, okay, and this device will use to monitor it. It will use to measure the voltage magnitude and the phase angle, and all the obtained signals, it is synchronized with the GPS technology. Now, so in this case, the main questions comes that why like phase angle is important. So as you are seeing in this figure here, that these are the two buses, like 1 and 2, and every bus has its own voltage, own phase angle. Okay. So as you know, as you are seeing here, the active power formula. So that is V1 V2 by sine phi 1 minus phi 2 XL. So as you are seeing that if phi 1 is equals to phi 2, so it means sine 0, and it means there will be no power flow in between line 1 and 2. So that's why this phase angle is very important to monitor, to observe continuously in power network. So okay, now in some books, some writers, they have used PMU as a synchrophasor. So you can also use synchrophasor. So now let's talk about synchrophasor. That synchrophasor is nothing but synchronized plus phasor. So first of all, we should know that what is the meaning of phasor here. So phasor means it is a pictorial or graphical representation of sinusoidal waveform, and from this phasor we can get magnitude as well as information of uh, phase angle. So as you are seeing in the slide that there are two forms, that is polar form and rectangular form. So both forms are acceptable, both formats are acceptable. But one thing is very important here, that rectangular form is more fast, it is more reliable. So mainly we are using rectangular form, not the polar form. Okay. Now see, earlier uh, uh, in power network, um, engineers, operators, they are using SCADA in order to monitor the system, in order to observe the power network. But in SCADA, there are some limitations. So in this slide, we are going to talk about the limitations of SCADA, which lead to the development of phasor measurement unit in around 19, 1989. So now SCADA. So what are the problems we are facing in SCADA? So as you are seeing in the slide, that these are the main problems. That is the main problem is here. That is 2 uh, just I have to use pointer here, laser pointer, right? So as you're seeing that 2 to 4 samples per cycle, the SCADA is measuring. But PMU is now it is up to 60 samples per cycle. But now if you see the latest paper, so they have written even 80 samples or even 100 samples per cycle. So in this case, what is the meaning of this 2 to 4 samples per cycle and 60 samples per cycle? It means that whenever there is a transient disturbance, suppose if there is a transient occurrence in the power network, so it may be possible that SCADA may overlook the transient problem. But PMU, it will measure the value in microseconds. It is very fast. So even for the transient problem, we can observe the value of with your PMU, we can observe the transient problem also. But in case of SCADA, it may not be possible. And also the one major reason of using PMU is that PMU signals are time-stamped signals. It is a time tagged signal because it is synchronized with GPS technology. But in case of SCADA, it is not possible. And one more important reason in case of SCADA and PMU is that SCADA will only measure the voltage magnitude, but it will not measure the phase angle. But in case of PMU has an advantage that it can measure both the values, that is your voltage magnitude as well as phase angle. But nowadays, IEEE has changed the definition that PMU can also, good for measure the value of Rokov, that is rate of change of frequency. So it is a new definition of PMU. Now, like earlier, that energy management system, it was started it around 1965, and at that time, data refresh rate. So it means the data means we are talking about the information here. So at that time, the information rate is around 2 to 5 seconds, but these signals are not synchronized. It means at that time there is no GPS technology, and also the problem of your state estimation in case of power network. So whatever the state estimation we are doing, the outcomes are not reliable. So for that, again, we are missing the point. Like at that time, we were missing the main important point, that is transient problem. So how can we overcome with the problem? And these are the reasons which led to the development of a phasor measurement unit. So okay, in 1970 also, in 1970 again, in case of interconnected power network, mainly we are using this phasor measurement system for again measuring the quantity of your electrical uh, systems. But in 1980s, when this measurement system, they have started using the GPS to synchronize the signal. So, like, what is the meaning of that time tag? It means time tag means like we are getting a signal at some time period. So at that time, it's particular time is a time tagged. Like suppose like you have used the Uber or Ola for booking your car. So at whatever a time, like suppose if in evening at 5 o'clock you are booking the car, so it means that 5 o'clock is your time tag. And let's take one more example. Suppose suppose if three persons are sitting together, and they are and suppose at an instant if you ask, so like if you ask them a question that okay you tell me that right now at the same instant what time your watch is showing. So maybe person A will say to you that 11:01, and at the same instant the person B will say to you that 11:02, and the same at the same instant again a person C will say to you 11:05. So now as you are seeing that 11:01, 11:02, 11:05. So and suppose if you're getting a data at 11:01, so okay, that is also one information. But at the same instant, how can we say that no, that 11:02 would be same, 11:05 would be same? No, because there is a time difference of zero point 0.1 second or zero point 0.3 seconds. So that's why all signals are synchronized with the GPS, because if the operator wants to see the data at 11:01 a.m., so he or she will look the data only at 11:01 a.m. from all over the centers. So there is no time delay and there is no time variations. So this is the timestamp. And this of PMU, advent of PMU, phasor measurement unit, is is comprised with this technology, with the GPS technology, and all signals are timestamped. And it was started, it was developed in Virginia Tech in 1988, and the first model is Macrodyne, and which was manufactured in 1992. No, so accuracy, as you see, as we have just talked about the GPS technology. So the accuracy of timing of GPS technology is better than 1 microsecond. So it is very good, because if we don't have a timestamp, then again there would be a problem of gathering the information. And also one thing more, that as just we have talked about the SCADA versus PMU comparison. So in that I have shown to you that the sample measuring of PMU is more, that is 30 samples per second. So because like in some of the new books, they have mentioned more than 60, more than 80 samples per cycle, second. So it is more faster than other things. Now, so this is a block diagram or functional diagram of PMU. So as you are seeing here, that this is analog inputs, anti-aliasing filter, okay, 16-bit analog to digital converter, phasor microprocessor, and modem. So like, okay, analog input means what? That we are getting the electrical quantity information from CT and PT. Okay, so all these information, all these analog information and analog input, we are getting from CT and PT, and again it will go to anti-aliasing filter. Okay, and it will weakens the signal layer, and it will go to your analog to digital converter, because we want to see the values in digital format, and again it will send this to the operator, to the energy management system. Actually, this block diagram of PMU is in general, because every manufacturer, they have different model. So this is the in general block diagram. Okay. Now, so PMU and Smart grid development. What is why how this PMU help in smart grid? So that is a very important factor, very important point in case of smart grid development. So as you know that nowadays even this that conventional infrastructure is now moving towards the modernization, because now the smart city concepts came, and this you know uh, removing, or you can say improving, improving of conventional infrastructure will leads to will leads to the idea of smart grid. And here we are using the phasor measurement unit in order to monitor, in order to observe the system information in dynamic way. It means it is in continuous way, and we can, and after after getting information, operator can take a right decision. So that is, and a right decision as well as accurate decision. So here reliability, efficacy, and effectiveness of PMU is very important in case of smart grid. So, okay, as we have just talked about that, the term smart grid means that a grid which works smartly. It means we are improving the conventional infrastructure of our electricity network. Okay, and we can, in case of smart grid also, we can monitor, protect, and we can optimize the operations by using stochastic and deterministic methods also. Okay, and okay, this is right. Yeah, yeah. So now, desired features of smart grid. What are the important factor in case of smart grid and why we want it? So first point, as you are seeing in the slide, that is advanced monitoring, control, and demand management. So as because smart grid is very accurate, it is very fast, and for smart grid, for in case of smart grid, we are using PMU, and PMU is faster than any other devices in order to gather the information of the network, and it can also identify the health of the network in dynamic way, and whether our system is working properly or not. It will give you all the information. So as you know that if you talk about the information, we are talking about the data of voltage magnitude and phase angle, because these two informations are mandatory in order to see whether our network is healthy or not. And also we have some advanced components in case of smart grid, and there are so many things involved, that is robust modeling and simulation tools. As in case of energy management system, we are using the simulation tools also. Okay, and this as and also as you know that now a smart grid is getting more complex because of addition of integration of renewable energy sources into the system. So it makes the system more complex. So again, there is a problem of monitoring and controlling of our interconnected power network. So for that reason also, PMU is better. So from this figure, we can try to get that what are the promising areas of smart grid development and its applications. So as you are seeing here, that generation and transmission. So in this case, we'll say wide area monitoring and control. So these two terms, as wide area monitoring and control, and also or distribution, industrial services. So all these area we can consider it as a information and communication technology, that is integration, because it is from generation to the user, from the to the customer. So that is information and communication technology integration. And also, as we have just talked about, that there is integration of renewable sources into the system. So this will from, because as we are using wind power, wind and solar also for the generation of power, and this comes under the smart microgrid. It's a new topic. Okay, and also for this area, transmission enhancement applications. So also by using PMU, by using phasor measurement unit, we can get information. We can get a proper information of transmission, whether it is a fault or whether it is the harmonic problems, or whether it is a radio interference problems. We can get all the information, all the transient information with the help of PMU. And also it will help in distribution grid management. Now they have advent new PMU, and it is known as the micro PMU, or distribution phasor measurement unit. You will find in some literature they have used micro PMU, and in some literature they have used the distribution PMU. So these two PMUs is used for the distribution observability. Okay, and also it is helpful for the advanced metering infrastructure, and EV charging infrastructure, and customer side system. Because at the customer side systems, what we want, what the customer wants, the customer wants the quality of power. Okay, so how can operator or companies or electricity companies, how they will provide a quality of power? So okay, by measuring, by solving the problem of a transient variations in case of system, by using PMU. So we can also improve that. Even a voltage divergence we can improve with the help of PMU, because we can get information in a very fast, and the information is very reliable. So in this way, like, we can improve the customer side problems. Okay, so now the deployment of phasor measurement unit, that is phasor measurement unit of wide area mounting and control. So this deployment of phasor measurement unit is, that is optimal placement of PMU or allocation of phasor measurement unit. So this work is done, like, is still going on, and from last 2 decades, many researchers, engineers, they are working on this field, allocation of phasor measurement unit. And why this topic is important? Uh, because the phasor measurement unit cost is very high, but nowadays even some companies, they have started making it cheap, but still it is doubtable. So still the cost is very high of phasor measurement unit. So that's why this allocation or optimal allocation of phasor measurement unit is required. And here in this figure, as you are seeing that blue dots, as you are seeing these blue dots show that here the PMU is installed in USA, United States of America. Okay. Now, potential, the promising application of phasor measurement unit. So, what are the promising area of PMU application? So, first one is wide area wide area monitoring. So, just I'll go back and we'll see this. So, as you are seeing that generation and transmission, wide area monitoring and control. So, as we know that this area is too much. Like, it is not a 10 kilometer, it is not a 5 kilometer, it may be more than 100 kilometer. So the coverage of area, this is the PMU will cover the large coverage of area, that is interconnected power network. And with the help of PMU, it is easy to monitor, it is easy to protect, and it is easy to control the connected power network in wide area or large size. And also with the help of PMU, that is we can also monitor We can also measure the value of angle and frequency monitoring, that is phase angle and rate of change of frequency, that is RUCOF, and inter-area oscillations and finding. Also, we can do with the help of PMU and voltage collapse. So voltage collapse is linked with your voltage instability problem. So again, with the help of PMU, as PMU has an advantage of measuring the voltage magnitude as well as phase angle. So with the help of PMU, we can avoid the voltage collapse also. And also the most important advantage of PMU is that is state estimation. So what is state estimation? State means we are talking about the condition. We are talking about the present condition of interconnected power network, and estimation means we are measuring the value of the current interconnected power network. And this topic of state estimation of PMU is very, very important. And for this only we are using the PMU, phasor measurement unit, for state estimation only. And there are more other, promising application of phasor measurement unit, that is fast frequency regulations. And we can also locate the transmission fault location estimations and dynamic model validation. And these are all some promising area of PMU applications. No, so from this figure, it would be more clear that how PMU is installed in real time. So as you are seeing that this is your transmission line conductor connected with CT and PT, and this portion is grounded, right? And these two input, that is electrical quantity, voltage and current quantity, it will go to your phasor. And again, this signal is a timestamp with the GPS technology, and it will go to the data center. So in this way, the PMU will work, and in this way, uh, uh, the operator or engineer, they will install the phasor measurement unit, and the analog input or electrical quantity is your current and voltage. Okay, and these two values are with respect to time. Now, so these are some of the important paper which I have gone through. So as you're seeing, that first important paper is by uh, Professor Baldwin. So Professor Baldwin has used graph theoretic procedure in order to find out the problem of optimal PMU placement. And again, B. Zhu and Ali Abur, uh, these are both are professors, scientists, and they have also find out the solution of optimal PMU placement problem using integer linear programming. And in this paper, they have considered two cases, that is absence and presence of zero injection buses. It means that if we are considering the zero injection bus, it means the problem leads to the non-linear problem. It is no more integer linear programming. It is the lead to the non-linear programming. So zero injection bus means when your neither load nor generator is connected at a particular bus, and that bus is termed as or known as zero injection bus. But in reality, it is like not possible, because every bus has a role to play. But as we are doing the this simulation in static information from static data, so zero injection bus is quite possible. Now, also in third paper, this is a paper of Professor Fadke, and Professor Fadke has also talked about the partial observability, that is depth of one unobservability condition and depth of two unobservability condition, um, while solving the problem of PMU placement. And in this case, that they have used the technique, that is again integer linear programming. Okay, and also in Dua and Dambade, uh, Professor Dambade has also given the idea of PMU placement, solving this problem by in the binary linear programming framework. So, sir has used the binary integer linear programming in order to solve the problem of PMU placement. And even B. Guo, sir has also used the integer linear programming in order to find out the optimal PMU placement problem, considering the different contingencies. So these are some important papers. So okay, I'll go to the next slide. Now, so objective. So first of all, what is the main objective of this topic, allocation of phasor measurement unit? The main, the main objective of this topic is that we want to monitor, we want to observe the complete power system network fully. Like we want to observe the power system network completely or entirely, and we also want that the method which we are using, it will give the guarantee of full observability of the interconnected power network. And as we have just talked that PMU is like expensive device, so it is unwise to place PMU at every bus of the electrical power system. So, and also the main problem is there that like how many PMUs uh, one should involve in one should install in IEEE 14 bus. Suppose if IEEE 14 bus system is there or IEEE 30 bus system is there, so how much at which buses and how many PMUs we are going to install in IEEE 14 or 30 bus system. So we will look for it in the next coming slides. And see, so the main objective of this topic till now that we have reached to the introduction part. So we have just talked about the introduction of PMU placement and what is PMU, why it is required, and how it is good for, and what is the effect of PMU in smart grid. So we have also talk about it, and we and in this topic we have I have used some of the system that is IEEE 14 30 57 118 and even northern regional power grid, that is NRPG 246 standard bus systems in order to find out the optimal PV placement problem. So we will see in the next slide. Now, so problem formulation and observability analysis based on phasor measurement unit. So this is also we'll talk about the problem formulation and also the monitoring analysis of phasor measurement unit. So as I was saying that I have just considered one small network so that we can understand it easily. So here, as you are seeing that IEEE 14 bus system single line diagram is given to you, figure 2.1 here for 14 bus system. And this G is a graph here, and V is vertex and E is edges. So vertex means we are talking about the node. So if you take IEEE 14 bus system, so it means that here 14 buses, 14 are nodes. So as you can count here, 14 are nodes, and edges means that is line, transmission line, and the total number of line in case of IEEE 14 bus system is 20. So as you are seeing here that bus number 7 is a zero injection bus, as I have used the static data which is available online. So here 7 is the zero injection bus according to the data which I have used, and it is available online. Now here, as you are seeing that this IEEE 14 bus system, we have make the undirected graph. So I just want to tell you again that graphs are of two type, that is directed and undirected. So Direction means that we are giving the path, we are showing the direction of the path. And here, as you are seeing, that we are not showing any kind of path here, as you are seeing in this graph. So this is called the undirected graph. So single line diagram, or if you want to draw a power system network in a graph format, so in that graph is always deals with undirected, there is no direction. Okay. And okay, so I have just given some important point here, that a node is observed if its voltage is knows, right? So node means we are talking about bus number one. So this is termed as node one, node two, node three. Okay, similarly, or till 14 nodes. And edge is observed if its current is known. So for edges, so PMU, what PMU will do? PMU will observe the voltage magnitude and phase angle of the particular bus, as well as the connecting buses and the branch current. Okay, branch current of the buses. So these are some problem formulations. So I just want to give you some small glimpse on these equations, that how these equations are working and what is the meaning of these equations. So as you are seeing that, first of all, dear students, one thing is very important here, that optimization is of two types. That is minimization problem and maximization problem. So here, the allocation of Phasor measurement unit in smart grid. This topic is based on the minimization problems. So here we are going to minimize the problem. Okay, so this function, as you are seeing, this objective function minimize I is equals to 1 sigma n, that is CIYI. Okay, so this n represents the number of buses in a system. So suppose if you take an example of IEEE 14 bus system, so this n is equals to 14, and the cost is for I. So I, again, the cost represents that if it is a 14 bus system, so we have assumed the matrix of 1 into n, that is your row vector, and yi is the binary decision variable vector. Okay, so this all subject to the constraint of h dot a dot y, and it is greater than or equals to b. So here h is the transformation matrix, and a is the binary connectivity matrix, and y is your binary decision variable vector, and b is your unity vector. So in this way, we will see, suppose if I and k are connected, so it means we'll take it as 1, and if I is equals to k, we'll take it as 1, and otherwise it is 0. So similarly, 1 means if PMU is placed, and 0 means that is otherwise, it means PMU is not placed. So I just want to show you from this graph that how this work here. So as you are seeing here, that if we consider bus number 1 here, so how can we form the binary connectivity matrix? So binary connectivity matrix, it means that is bus to bus connection. It means vertex, also you can say vertex to vertex connection, or you can also say nodes to node connection. So it means that if I say bus number 1, so bus number 1 is connected to 2, bus number 1 is connected to 5. Okay, so it means that these two connection will leads to this your matrix, that is n into n. This is your a matrix, that is node to node. So it means bus number 1 itself, so we are considering as 1. Bus number 1 is connected to 2, so okay, it is also 1. Okay, and bus number 1 is not connected to 3. So as you can see in the figure here, bus number 3, okay, so 1 is not connected to 3, so it means we are taking here 0 0. So similarly, for bus number 4 also is not connected to 1. Okay, so here we are taking 0, and bus number 5 is connected to 1, so we are taking 5. So we can go again back to the figure and we'll see whether it is true or not. Yes, it is okay, right? 1 is connected to 5. So so according to the equation, according to this condition, we can say that yes, it is true. So this matrix is 14 by 14, 14 by 14 matrix. It means that as you are seeing that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so 14 buses. It means one, this represent one bus, two, three. So likewise here also 1, 2, 3, 4. Okay, so till 14. So 14 by 14 matrix. So in this way you can make the this matrix, binary matrix. Now, so let's take an example. Again, we have taken a 14 bus system here. So if we talk about the constant, so as you are seeing that it will form a 14 equations here. That is like according to this equations. Okay, so we will form the equation. So it means as you're seeing that f1 equals to y1 plus y2 plus y5. It means that as you are seeing that y1 plus y2 and these are 0, so plus y5. So similarly for bus number 2, the function is y1 plus y2 plus y3 plus y4 plus y5. And for f3 is y2 plus y3 plus y4. You can see here f3, that is this is y2, y3 and y4, and all the buses are 0. Okay, and so on and so forth. You can count it. So now what is the meaning of this equation? What is the meaning of first equation? Okay, now let's see that this equation shows that if you want to monitor bus number 1, okay, if we want to observe bus number 1, then PMU must be placed either at 1, 2 or 5. Okay, it means if you want to monitor bus number 1, we have to place PMU either at 1, 2 or 5. It means any of these three we can place PMU if you want to monitor bus number 1. Similarly, for bus number 2, if you want to observe bus number 2, then PMU must be placed either at 1, 2, 3, 4 and 5. And likewise for bus number 3 also, if we want to monitor bus number 3, then PMU must be placed either at bus number this 2, 3 or 4, and so on and so forth. So this is the meaning of these equations, and this is a normal operations. Okay, so in this way we will solve the problem of OPP problem. So here, as I have already mentioned here, that operator plus serve as a logical OR. Okay, so I have already explained here. So we'll, okay, now as you're seeing here, if the zero injection bus involved, so here we are saying that this is a zero injection bus, bus number 7. So these are the connection. This 7 is connected to 8, 7 is also connected to 9, and 7 is also connected to 4. So this will change as F4 is Y2 plus Y3 plus Y4 plus Y5 plus y7 plus y9 plus f7, 8 and 9. So this is the equation. So we can take the value from here, that is you can take from here, that is f7, f7, f8 and f9. Okay, similarly for f8 is y7 plus y8 plus f4, f7, f9, because f4 is, if we consider f4, then we are taking f7, f8 and f9, right? And if we are considering f8, then we are taking f4, f7 and f9. And if we are considering f9, then we are taking f4, f7 and f8. Okay, so in this way this equation developed for the zero injection buses. So we can take a value of f7, f8 and f9 and we can put it here. Like if we see f7, so what is the value? F7 is y4 plus y7 plus y8 plus y9. So we can go back and we'll see whether it is true or not. So f7 value is y4 plus y7 plus y8 plus y9. So what we are doing, we are just simply putting the value here and we are solving it. Okay, So after solving we'll got y2 plus y3 plus y4 plus y5 plus y7 plus y9, that is y8 dot f8 dot f9. Okay, and also for f4 we can further minimize this problem. So we are again minimizing it. So the final equation is y2 plus y3 plus y4 plus y5 plus y7 plus y9 and y8 point f9. Okay, and for f9 similarly we have find out this value, that is for f8 is y4 plus y7 plus y8 plus y9. Similarly for f9 also you can solve, and the equation is y4 y7 y9 y10 y14 y2 dot y8 plus y3 dot y8 plus y5 dot y8. So now this is a constraint, because we have changed. We are considering the zero injection bus. So I'll just go back and I will. Okay, so this equation 2.6 equation is for the normal operation, when we are not considering, when we have not considered the zero injection buses. It means that here we are ignoring the zero injection buses. Now let's go back to the equation once again here. So what we are doing here now, we have considered the effect of zero injection buses. So when we have considered it, so your F4, F8 and F9, these values are changed. Okay, and you are seeing that we are not considering F7 here, because we have taken F7 bus number 7 as a zero injection bus. Okay, now a PMU outage. So this is also one constraint. As you know that PMU is a device. So every device will have some malfunction problem. Okay, because it also get involved in a problem. So as like I'm sure that in case of switch gear and protection, there is a coordination of relays. That is, we are using. Suppose if one relay out, so we are using the secondary relays in order to provide the backup, and we say that that is a backup relay. So in same case in PMU outage also we are using two PMUs. That is, first one is your primary PMU and second one is your backup PMU. So what does it mean? Suppose if primary PMU get malfunction or failed, then backup PMU will come into picture, and it will monitor, it will do their jobs. Okay, so for that, so what is the equation when whenever we are considering the problem of PMU outage? So what are the equations we have to keep in mind? So here, as you are seeing, that F1 is equals to y1 plus y2 plus y5 is greater than equals to 2. So this 2 represents that suppose if bus number 1 fails, then 2 PMU is required in order to monitor the bus number 1. It means that if, because earlier, as you are seeing here, we'll go to the normal case here. So earlier, as you are seeing here, we are using the 1. So this 1 is, according to this equation, B. So this is a unity vector. Okay, so this B is a unity vector. Here I have mentioned already. Okay, so in this way we'll font. So it means that if we are talking about the 14 bus, so it is 1 into 14 matrix, that is vector. Okay, so similarly for 2, so it means if we are writing 2, it means we are talking about the PMU outage, and here that if one primary PMU fails, then the backup PMU will come into picture. So this is represented by a 2 here. So here this B matrix will become 2. Like here in the normal case, we have taken one unity vector, but here we are considering 2 in case of PMU outage. Now, again, the problem happens because let's say talk about the line outage. Okay, so now let's see that here line 4 5 it get failed. Okay, so how this constraint will come? So we'll see here that there is some change in 4 and 5. We'll see what are the changes. So as you are seeing here that F4 is y2 plus y3 plus y4 plus y7 plus y8 is greater than equals to 1, and F5 is y1 plus y2 plus y5 plus y6. So we'll go back again in the normal operation and we will see whether there is any some changes or not. So we'll see, we'll go again to the normal operations. Again, I'm going back and we are seeing that F4 is y2 plus y3 plus y4 plus y5 plus y7 plus y9, and F5 is y1 plus y2 plus y4 plus y5 plus y6. It means that there is some changes as you are seeing here in the slide, that there is some change. Okay, because this line is removed. This line has some severe damage. That's why we have removed this line, and it will also affect our constraints. Now, this is the next topic, that is complete and incomplete observability. So as you are seeing here that this red dot, these red dots, this will show the PMU install at bus number 2 and bus number 5. And here in figure B and figure C, the PMU is installed at bus number 1 and bus number 5, and in figure C the PMU is installed at bus number 2 and bus number 4. So red dot is showing that these are the PMU equipped buses. Now let's see from figure A here that if we install PMU at bus number 2, then we can easily monitor the bus number 1, bus number 2, bus number 7, and also bus number 3. Okay, because these are all interconnected, right? So we can easily monitor by one PMU. And if we install PMU at bus number 5, then we can easily monitor bus number 4. So it means we can say that for 7 bus system, only 2 PMU is necessary in order to observe, in order to monitor whole network. So as you are seeing that only 2 PMU is required in order to monitor the 7 bus network. Similarly, if you talk about the in case of B here, that if we install PMU at bus number 1 and bus number 5, then you are seeing here that PMU will only observe, monitor bus number 2 and bus number 7 only, and bus number 5 PMU is only monitor or observe bus number 4 and 6. But this number is left. So it means we can say this is the problem of depth of unobservability 1, that is incomplete observability. It means while installing PMU also our one bus is left in order to we are unable to monitor bus number 3 after installing 2 PMUs in 7 bus system. But now let's take figure number C here, that as you are seeing that PMU is installed at bus number 2 and bus number 4 also. So with the PMU installed at bus number 2, we can easily monitor, we can easily observe bus number 1 and 3, and also with 4 also we can observe bus number 3 and bus number 5. But the problem is that B6 and B7s are unobservable. So this yellow point is showing that these 2 buses are unobservable, and this case will lead to the depth of unobservability two condition. So here 1, it means depth of unobservability 1, and here 2 are left. It means it will termed as depth of unobservability 2. So this is the problem of complete and incomplete observability. Now let's talk about some rules that how we are going to place PMU. This is a very important part in order to place PMU in interconnected power network. So as you are seeing that I have taken this four bus examples here, that is 1, 2, 3, and 4. Now, so if we place PMU at bus number 3, then we can easily monitor bus number 1, bus number 2, and bus number 4, and even bus number 3 also, because it is, installed, this bus is equipped with PMU. And also see, uh, in figure B, it is a condition here that if zero injection bus, if bus 3 is a zero injection bus, and we have installed PMU at that bus. So again, and it will observe bus number 2 and bus number 3 and bus number 4. And suppose if bus number 1 is not observable, then we can observe by using the KCL. Okay, because this is just an assumption. Now similarly for rule number 3 here, for rule number 3, suppose bus number 3, again we have assumed that bus number 3 is a zero injection bus, and here suppose if bus 3 is unobservable, and bus 2 and bus 3, bus 4 are observable by PMU. So this bus can be observed by using the KCL. Okay, and now rule number 4 goes to your radial bus. So suppose if PMU is installed at bus number 1, so only bus 1 PMU equipped, only it will monitor bus number 2, but it will not observe the radial buses. So it means again we can observe this radial buses by using the KCL. And this is rule number 5, that if it is a zero injection bus and there are maximum number of connections at this point of bus, so we can say that here also we can install PMU. Okay, and we can also monitor all the buses connected to the zero injection bus with the help of PMU. Now this concept radial buses, what is the meaning of it? It means that there is only one connection with this bus. So we'll go back to IEEE 14 bus systems, and we will identify that which bus is a radial bus. So I am going once again back to the normal operation slide, and we will see that which bus is a zero injection bus. So now here again, I'm at figure 2.1 here. So as you are seeing that bus number 8, 7, right? So this bus we have termed as zero injection bus, and bus number 8, because there is no further connection, so we can consider this bus as a radial bus. So it means in IEEE 14 bus system, only one bus is a radial bus system, that is bus number 8. Now let's go back to the slide. Yeah, so we have just completed. Now, again, there is one important part here, that is redundancy measurement. And in case of placement of PMU, this will help to find out the best solution, best set of solutions. Okay, so now as you are seeing here that bus observability index, that is BOI, in some of like many of the literatures, they have used the BOI, bus observability index. So what is the formula? That is A matrix into N matrix. So A matrix is your binary connectivity matrix, and N is your solution strings. Okay, of this is a NPMU, means that this will show the solution strings. Okay, and if we multiply these two matrix, so what we will find out? We will find out this value here, that is 1 1 1 3 2 1 2 1 2 and 5 ones. Like, what is the meaning of it? So this is showing bus number 1, bus number 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So what is the meaning of it? See, It means that if we placed PMU at the location 2, 6, 7, and 9, okay, if we place the PMU on 4 location, so we can observe our network completely. So this BOI shows that after placing 2679 PMU, we will observe bus number 1 time, bus number 2 1 time, bus number 3 1 time, and bus number 4 3 times. Okay, bus number 5 2 times, bus number 6 1 time, so on and so forth. So with the so it means that if we install PMU at 2, 6, 7, and 9, at this is the best location. So we can monitor, we can observe whole IEEE 14 bus system. Okay, so this is the meaning of this bus observability index. Now let's talk about the system observability redundancy index. So in this case, what we are doing, so we'll find out. See, so I think this is clear to you. That is BOI is equals to A into NPMU. So this will clear to you already. This will shows the optimal location of PMU. This is a string. Okay, this is a solution. After using your technique, you will obtain this solution in such a way. And after multiplying with your binary connectivity matrix, you can obtain this vector, you can obtain this equation, right? BOI. So now SORI. So what is the meaning of SORI here? Like we are summing it up. So when we sum this up, we will find the value that is 19, right? So SORI is equals to 19 means we have sum like 1 plus 1 plus 1, like so. If you solve it, you will find 19. So why this method is required? This is the important part. What is the use? Why we are doing this nine, and what is the meaning of 19, 16, 16, and 14? What is the meaning of this? I just want to tell you that see, optimal PMU placement problem is a combinatorial optimization problem. It means there are multiple solutions. Okay, there is no single solution, there are multiple of solutions. So out of these multiple solutions, we have to choose the optimal solutions. Okay, out of multiple set of solutions, we have to choose the optimal solutions. So for optimal solutions, this SORI, we have taken the help of SORI. Like how? So as you're seeing here, that this is, we have taken one assumptions that 2 6 7 9 is one set, 2 7 11 13 location is one set, 2 7 10 13 location is set number 3, and likewise 2 8 10 13 is set number 4. So now in this case, as you are seeing that S1, so set number 1, the value is 2679. This is the optimal location. So we will find out after summing this up, we are finding SORI is equals to 19. Okay, this is set number 1 solution. Set number 2 solution is 2 7 11 and 13. So after, like, as you sum all this your BOI, then you will find the value 16. And similarly for S3, you will find out 16. And similarly for S4, the location is 2 8 10 13, and then the SORI value is 14. So as you are seeing that we have 4 set of solutions, and the maximum SORI is we are obtaining with the set number 1, that is solution 2679. So we can say that 2679, that is set 1, has higher SORI value. So it means that this set number 1 is a optimal solutions. Okay, so it means that higher the SORI value, more that set of the solution is optimal. Okay, so this is the important part of SORI value. Now, so summary, like till now, what we have talked about, that we have talked about the problem formulations and observability analysis, and also we have talked about some of the important points of PMU placement rules, and in order to find out the optimal PMU placement problems. And we have talked about some various contingencies, that is your zero injection bus, line outage, PMU outage, and partial observability, that is a depth of 1 and 2 unobservability conditions. Now let's talk about the BPSO technique, that is boundary particle sum optimization technique, which is used for the optimal placement of PMU here. So in this case, as this boundary particle sum optimization technique is introduced in 1997 by Dr. Kennedy and Dr. Eberhard, and this will use in the discrete search space. So here I have just taken one example here, again, 7 bus system. So as we have just discussed, that if we place PMU at bus number 2 and bus number 4, then it will observe whole system, right? So it means this gray sign is the complete observation of PMU, and this green sign shows that these two buses are equipped with PMU. So again, the solution. So it means that here the dimension of the particle is 7. Okay. So it means, because if you are taking 7 bus system, so it means the dimension of the particle is 7 here, and it will comprises 7 number of bits. Like if you are going to increase the system, so your particle is depend upon the size of the system. Suppose if you're using 14-bus system, so the particle size is 14. If you are increasing the system, 30-bus system, so your particle size is 30. So like that, so on and so forth. Okay, so this is a string solution, that is 0 1 0 1 0 0. It means that 0 means bus number 1, 2, 3, 4, 5, 6, and 7, and we can say that PMU is placed at bus number 2 and bus number 4, if we take an example of 7-bus system. Now, these are some of the important equation of boundary particle sum optimization. And okay, I'll just discuss these equations here. That is, this is your velocity of your boundary particle sum optimization. Okay, and see, there are PSO and BPSO. This is very important point here. That what is the difference? The main difference between particle sum optimization and boundary particle sum optimization is that it is in the position update function. It means that that the next position of BPSO is not influenced by the present position. Okay, so it will not influence the present position in case of BPSO, but in case of PSO, it is there. So this is the equation here. This part is showing the momentum of the particle. This is the cognitive component, and this will show the social component of your particle sum optimization. Now particles. So we have talked about we have already discussed about the particles here, that every particle. So particle, it means that if we are taking a bus 7, so here the particle is 7, right? So as you are seeing here, that bus number B1, B2, B3, B4, B5, B6, B7 is the particle here, and this number showing the strings, that is 0 1 0 1 0 0. So this is a string solutions of 7-bus system. Now fitness function. So in PSO, in BPSO, the fitness functions play a major role. It has to play a major role here. So in this case, the fitness function involve three major rules. First one is, like as we have just talked, that we are talking about the observability of the connected power network. So this is one constraint. Second one is we want to minimize the number of PMUs, and the third one is redundancy measurement. As we have just talked here, I'll just go back and again I will give you the meaning. So this, I'm talking about the redundancy measurement, that is bus observability index and system observability redundancy index. Okay, so this is the redundancy measurement. Yeah. Okay. Now, so what is the formula of fitness function here? So in this way, you can form the formula, that is W1 into N of. So this is a total number of observable buses. This is total number of PMUs. plus redundancy measurements. That is ranking, because as you know, as just I have said to you, that optimal PMU placement problem is a combinatorial optimization problems. So on the basis of that, we have to consider the redundancy measurement here, because there are different solutions. There are not a single solutions. There are multiple solutions. So with the help of this measurement, we can identify the optimal solutions. Okay. Now, so case studies. This case study is given here. That what are the population size I have taken. So this I have done on 14 bus system, 30 bus system, 39 bus system, IEEE 57 bus system, IEEE 118 bus systems, and Northern Regional Power Grid 246 bus test system. So here I have taken the population size of BPSO is n into 20. That is, n is a number of number of buses in the system. And here the cognitive parameter I have taken the same, that is 2.04 and 2.04. Okay. And here the initial parameter I have taken zero point 0.9 and 0.95. So these are the test systems data specification. That is a test system I have used at IEEE 14 bus system, 30 bus system, 39 bus system, at IEEE 57 bus system, 118 bus system, and Northern Regional Power Grid 246 bus system. So here are the number of branches information. That is, for IEEE 14 bus system, the number of branches is 20. Similarly, for IEEE 30 bus system, it is 41, and 39 bus system, it is 46. For 57 bus system, the branches is 80, and for 118 bus system, the branches is 186. Similarly, for Northern Regional Power Grid 246 bus system, the number of branches 376. No, so these are the location of zero injection buses. As we have just talked, that IEEE 14 bus, in IEEE 14 bus system, the bus number 7 is a zero injection bus. Similarly, for IEEE 30 bus system, the number of zero injection buses is 6, followed by New England 39 bus system. It is having 12. 57 bus system has 15 zero injection buses, and IEEE 118 bus system has 10 zero injection buses systems, and NRPG 246 bus system has 60 number of zero injection buses. And again, in this table 3.4, we'll see about the location of radial buses here. So in this case, that IEEE 14 bus system has one radial buses, as I have just informed to all of you. That bus number 8 is the radial bus in case of IEEE 14 bus system, and also in IEEE 30 bus system, the number of radial buses is 3. So that is 11, 13, and 26. And for New England 39 bus system, that is number of radial buses is 9. So on and so forth. This information is given. Now, so what are the important locations in case of normal operations after using the binary particle sum optimization technique here? So there are a number of trials, that is 10 trials. So what I have found out that 2679 is the best solutions. So okay, 2679, and because there are multiple solutions, so on the basis of SORI value, we have reached to the conclusion that 2679 is the optimal location of PMU in case of IEEE 14 bus system. Now for 30 bus system also, we have gone through number of solutions. So again, we have observed that 1, 5, 10, 11, 13, 15, 16, 18, 27 is the optimal locations. So similarly for New England 39 bus systems, I have shown. For 57 bus systems, I have shown here. And for 118 bus systems, I have also obtained, because there are so many solutions, but we have choose only the best solutions for the placement of PMU in IEEE 118 bus systems. Okay, and also in case of Northern Regional Power Grid, I have gone through so many solutions. but we have choose only the 10 solutions based on the SORI value. And okay, so these are the optimal locations under normal operations, which we have obtained from the binary partition optimization technique. That is 2679 for 14 bus systems, and 9 buses is in case of 30 bus systems. 9 is also in 39 bus systems. 11 in 57 bus systems. 32 is in 118 bus system, and 60 is in 246 bus systems. And also in case of considering the zero injection bus, we have find out that 2679, because we are not considering 7 in the solution, as 7 is a zero injection bus. So again, the number of PMU is reduced. So as you are seeing that, if we are considering the zero injection bus in case of 14 bus system, so the solution is reduced to 3. So it means that again we have minimized the use of PMU. So similarly, we have considered zero injection buses for all the test systems, and we have observed that there is a minimization of PMU is involved whenever we are considering the zero injection buses. So this in this table we have compare our results with the state of art literature. So what we have find out that okay, that 4, 9, 9, 11, 32, 60, we have obtained the solution for 246 bus systems. Now, so what is the summary of this topic? That we have, used the binary particle sum optimization technique in order to solve the problem of optimal PMU placement problem. And again, our main objective is to maximize the redundancy measurement, and also we are planning to, successfully uh, implement this BBSO technique to larger size of the network. Now again, weak bus constraint PMU placement for systems observability. So in this case, weak bus means that a bus there is a maximum voltage variations due to changes in the system because of the load increase or some other fault or some contingencies. So these are all some reasons which leads to the normal bus as a weakest bus. So our in this topic, topic, the main objective is to first find out the weak buses, and we are going to install the PMU at this weak buses. This is the main objective. So now, as you're seeing, we have used one line stability index method to find out the weak bus problem. Okay, so in this case, we have used MAD power also, MAD power 5.1, in order to do the load flow analysis. And after finding the load flow analysis, we have used the line stability index method in order to find out the the weak buses. And one thing is important here, that if see this last point here, that if this value, that is line stability index value, is less than 1, then the electrical network is said to be stable. But when this index surpasses the value of 1, it is then the network is unstable. So on the basis of this, we have find out the weak buses. Now here we have used the method binary integer linear programming. Here we have used BILP. So as you are seeing that this is the normal bus system, that is a 8 bus system we have used here. So this green sign shows that on bus number 2, bus number 4 and 7 PMU install. So this is a normal case. And again, we have considered, we have assumed that suppose if bus number 2 and bus number 6 is a weak buses, so we have to give them the priority because they are the weak buses. So we have to give them the priority. So what we did, again we did the simulations. So we have find out that bus number 2 is weak buses, and we are successfully install PMU at bus number 2, bus number 6 also, and bus number 4 and 7. So this is our main objective, that we want to monitor the weak bus directly. This is our main objective. Now, this is the next, because that method is same, because here we are again we are going to find out the binary connectivity matrix. Okay, that is 1 1. So this is 8 into 8, because as we have taken example of 8 into 8 matrix here, 8 bus matrix. Okay, so this will leads to same formula, that is f1 equals to y1 plus y2, f2 equals to y1. So these are the same. Okay, I'm not going to discuss this. This is also same. Okay, because we have, this is your a matrix, this is y matrix, and this is your b matrix. So this is same. Okay, so this is also same, because here we are considering the weak bus measurement, and we have considered here that bus number y2 and bus number y6 is always 1, because these are weak buses. So we can't make it 0. Y2 and y6, we can't make it 0 because they are weak buses, and we have to give them the priority. Now, so these are all same, right? For 14 bus system, location of zero emission buses is 7 and 8. So these are these information is same. Okay, same. Right. Okay. Now here, as you're seeing, that in table 4.2, we have used the line stability index method in order to find out the weak buses. So here for 14 bus system, the weak bus is 7, 11, and 13. Okay, and for 39 bus system, we have taken 4 weak buses, that is 16, 19, 20, and 22. Similarly, for 118 bus system, we have chosen 6 as a weak buses, that is 23, 29, 64, 86, 96, 108. And for 300 bus system, we have chosen 10 weak buses, that is 73, 78, 91, 189, 198, 229, 231, 245, 246, and 283. So these are the systems. So after ignoring and considering the buses, we have find out the solution, that as you are seeing, that this result, this result is a normal operation result, and this result we have considered the weak buses. So as you are seeing that there is a change in the location, because this is a normal operation 2, 6, 7, 9, and here 3, 5, 7, 10, and 13. So if you look here, that 7, 11, 13. So what we want to monitor these 3 buses directly. But okay, I have achieved that 3, 5, 7, 10, and 13. So we are monitoring here 7 and 13 directly in case of 14 bus system. And similarly, we can see in 39 bus system also. Okay, and for 118 bus systems also. So there is some increment in uh, number of PMUs, because as we are seeing that if you talk about the normal operation, then the location is only 4, but here if we consider the weak buses, then location is 5. Now, this is the problem when we are considering the PMU whenever there is a single PMU loss or PMU outage. Okay, so if we are not considering the weak buses, then the PMU loss, like PMU loss in 14 bus system. So what is the impact? So the location which we obtained is 2, 4, 5, 6, 7, 8, 9, 11, and 13. But if we are considering the weak buses during the PMU loss, then the location is 2, 3, 5, 6, 7, 8, 9, 11, and 13. And here only, here this 4 is changed. Otherwise, the counting is same. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 numbers. And here also 1, 2, 3, 4, 5, 6, 7, 8, and 9. But only the thing is what happened that there is some change in the location. So similarly for 39 bus system and same for 118 bus system and for 300 bus systems also we have find out the location with single PMU outage considering and ignoring weak buses. So okay, we have just find out this number here that during the normal operation that is 4, 13, 32, 87. But whenever we are considering the weak buses, when there is no PMU loss, then the equation is 5, 14, 32, 88. And for ignoring weak buses, the this choices is 9, 28, 68, 202. But in this case, if you are considering, so for 14 bus system, it is same, but there is a change in location. But for 20, for 39, 118, and 300, it is increased. Like see here 28, it is 29, but for 118, it is same. And for 300 bus, the number is increased to 1, that is 203. So this is based on your weak bus formulation whenever we are considering the weak bus or not. Now complete and incomplete observability, as we have talked about that that if there is one bus left unobservable, then it will treated as depth of one unobservability condition. And when two buses left unobservable, then that system will consider as depth of two unobservability conditions. So this again we will talk here, and here we have considered the partial observability with single PMU outage and also with single branch outage and also with the PMU outage and branch outage. Now, so here the concept is same. Like again, we are showing again. I have used the BILP here. Okay, so this is 14 bus 14 into 14 matrix, and this is subject to the constraint that is y1. Okay, so this is a, this matrix whole is a, this is y, and this is b matrix. We have taken two. It means we are talking about the PMU outage. Now, so let's take here. If we find out the depth of unobservability one, then this is the objective function, and this matrix will come into picture. That is C1. Otherwise, everything is same. Okay. The only change is C1. So, what is C1? C1 is the binary connectivity matrix of the line to node. Now, this binary connectivity matrix is based on the line to node, as we are seeing here that this is L1 and this is bus number 1, 2, 3, 4, like 14 bus system, and this is 20 lines. So this size of the matrix is 20 into 14. So right, every line 1 is connected to 1, 2. So like that, this equation, this matrix we can obtain. And here we have used the bin prog toolbox in order to solve the this problem, right? Now let's talk about the depth of one whenever there is a whenever we are considering the outage. So this is when we are not considering the outage. As you are seeing that B is not multiplied with 2, but here we are multiplying with 2 because we want to see that how depth of unobservability 1 will behave whenever there is a single PMU outage. So we have multiply with 2 in that case. And now case is depth of unobservability 2. So as you are seeing that this here C2 matrix is important. In this case, C1 matrix is important. So what is C1? C1 is the binary connectivity matrix of the line to node. So I have shown you here. But in this case, C2, okay, so in DOU2, in this case, C2 matrix is very important. So what is C2 matrix? C2 is a binary connectivity matrix of all possible combination of three buses connecting together. Okay, so this matrix will give you the three that buses connected with three buses. Okay, and we can also obtain this DO2 whenever there is a outage, whenever there is a PMU outage. So by multiplying this D2 with the 2, we can easily obtain the result, the outcome of DOU2 with single PMU outage. And here this matrix, the size of this matrix is 26 into 14. This is the size of the matrix of C2. Now this the second case is considering zero injection measurement, because here we are considering the zero injection bus. So how? Because in these cases we have not considered the zero injection bus. Okay, but now the case 2, here we are considering the zero injection bus measurement. So as you are seeing that how it is behaving, again we are subject to these equations only change. Like you don't have to change anything, but you have to include some of the vector or some of the matrix here. Okay, so PR1, because C1 you know already, so PR1 is a probability matrix. Okay, and similarly here PR2 is one multiplied, that is it is PR2 is a matrix that remove branches which is not connected with zero injection buses. So only these two changes are there whenever we are talking about the consideration of zero injection buses. Now, so these are some data information. So this is same already I have shown you. So, okay, these are the locations. This is for the normal operation, and this is for when we are considering the zero injection buses. So I have already shown. Now this is the result of depth of unobservability 1. So 14 bus system, that is 4 6. Okay, 4 6 4 6 as you are seeing. So this, and whenever we are considering the zero injection buses, so here it is changed, that is 5 9. And similarly you can see for 30 bus system, 39 bus system, and so on and so forth. And also we have talked about here that this problem here we have considered the single PMU outage with the effect of zero injection buses. So as you are seeing that here uh, during the whenever we are not considering the zero injection buses, the solution is 9. But if we are considering it, the solution is 7. So similarly, as you are seeing that there is some reduction in case of PMU, that is 21 15. For 39 it is 28 17. For 57 it is 33 and 25. And for 18 bus system 68 and 61, right? So I'll go back. So this is the result of optimal location of PMUs considering the PMU outage. So I just seeing here that 2469 4610, okay, and 210 13 4 11 13 is the solutions. So you can see for all the systems here, even in this case also, because we have taken the critical branches. So suppose if you are taking 9 and 10 as a critical branches, again for with the help of line stability index, so we can obtain the solution, that is 2 8 9 11 and 13. And if we are considering the critical branch 6 and 13, so the solution is 4 5 6 8 9. And if we are considering line 1 2 as a critical branch, then the solution is 4 5 6 8 9. Okay, so similarly you can see here, this is for the whenever we are considering both the PMU outage and critical branches, so the solution is in front of you. That is there are 10 locations. Okay, and here it is 5 location, and here it is 10 locations. Okay, so you can go, you can see here all points. So now this we have compared with so many papers. So we have find out that our solution is robust because it is good for all the systems, and it can handle even 300 bus systems at a faster rate at a reasonable time. It gave the solutions of PMU placement problem. So our system is good. Our method which we have used to find out the solution is good. And these are all the the comparison while considering and ignoring the zero injection buses. As you are seeing here, that proposed method has outperformed the result. It is somewhat better than other results. And in this case also, some of in many papers, they have not talked about the 246 bus system, and we have used, so 153 and 187 is the solution. And here we are seeing the 68 and 61. So some of 61 is also the some of the authors they have achieved, and 64 is achieved also, but this is not the optimal solutions. Okay. So again, we have done some comparison during the branch outages. So again, we have find out that our solution is outcome all the problems. So here you're seeing that 5 is for 14 bus, 30 bus 10, right? 39, 14. So similarly, we can see that these are some solutions. So here also, this is for the single PMU and branch outage. So okay, this is also somewhat reliable. So in this topic, we have to talk about the partial observability, that is DOU1 and DOU2, and I have shown you some mathematical model that how we can draw the problem of DOU1 and DOU2 and how we can solve it. And we have taken some of the important constraint, that is single PMU outage, branch outage, single PMU outage, and both we have considered together in order to find out the effect of solutions for OPP problem. And here we have used the binary integer linear programming formulations in order to find out the problem. Now, two-stage branch and bound we have talked. Now, this time is less, but I'll try to complete this. So here we have used the branch and bound. And as you know, as I have just discussed to you, that optimal PMU placement problem is a combinatorial optimization problem. It means we are not getting only a single solution. We have a multiple solutions. Okay, so for that we have used a branch and bound algorithm, and branch and bound we have implemented with the Tom lab and mixed integer non-linear programming branch and bound routines. And the main aspect, the main objective of this two-stage branch and bound is that we have used two stages. First one is that first it will explore the tree with the help of depth first search method, and second it will find out the basic solutions by using the best first search method, and it will only search the most appropriate node in case of network. So I just want to give you example here. I have just taken this small system here. So suppose in stage one, what will happen? So first, in case of, suppose if you are using depth first search here, so depth first search will go to 1, but it will not explore. It will not explore. Again, it will go further, and again it will not explore. Again, it will go to 3, and again it will come back to 2, and again it will go to 6, and again 7. So like that. So this is the process of depth first search method. Like, it is not going to explore this node. It will go directly to the second node. And what the second stage will do in that stage, best first search, it will first come to 1 and it will observe the node. It means it will observe 5 and it will observe 4. Like, it will visit to 5 and 4 from here only, and again it will go further, and again it will visit 7 and 6. So again it will go to 3, and again it will come back to 2. It will not go to 6 because it is already observed, because it is already visited. So in this way, we have implemented the two-stage branch and bound algorithm. Now we have taken one example of AWT 14 bus systems again, and we have found out the spanning tree here, that is branch and bound spanning tree. So as you are seeing this tree here, that if we talk about the bus number one here, so bus number one is visited to two, and is it is directly connected to five. So you are seeing that two and five, and again if we explore two, so if we explore two, then two is connected to directly to 3 and to 4, right? So 2 is connected to 4, and 2 is also connected to 5, but it is already observed. So we this dotted line is showing the twig here, right? So similarly, we have made this spanning tree with the help of your IEEE 14 bus system, and we have used here some solver, that is intlin prog, bin prog, CBC. There is coin branch and cut, SCIP solver, GLPK, linear programming solver. So we have used so many solvers in order to find out the problem of PMU placement. The objective is same as we have as I have shown you in the problem formulation topic. Okay, so here we have used the mixed integer non-linear programming model for the solution of zero injection buses, and these are the results which we have obtained. So as you are seeing here, that result for int lin prog, we have observed 2, 8, 10, and 13, 14, but it is not optimal because by using bin prog we are getting 2, 6, 7, 9, that is 19. So this solution here is not uh, not optimal. So we have checked all the solver, intlin prog, bin prog, and also CBC solver. I have used SCIP, I have used 2, 7, 10, and 13, but again these are not the optimal solutions. So again, we have used GLPK. So this is okay, 19 solutions. This is also coming 90 solutions, but for higher system it is not good, because for 30 bus system it is giving 51 SORI value, and here it is giving 50. So this is not this solution with the help of GLPK. We are not getting optimal, but in some cases it is okay, because here as you are seeing that for 246 bus system, GLPK is better. It is giving 343 solution, but LP solve is not good because it is getting only 329. So that's why we have chosen all the solvers in order to solve, right? And also in 14 bus systems also, as you're seeing that there are multiple solutions. So we have do the SORI value. So according to the SORI value, we have reached to the conclusion that 2679 for 14 bus system is most optimal solutions. So similarly, we have shown the result for all test system, that is 246 bus systems also. We have find out the SORI value. Okay, and also we have taken the zero injection bus. So as you are seeing that there is some changes in the number of PMUs. Okay, and also 246 bus system we have chosen. So again there is some changes, that is 62. As you are seeing here, this is a 62 numbers total. Okay, so now this is ignoring zero injection buses and considering zero injection buses. So again, this result we have obtained from using the binary integer linear, a branch and bound with the help of your mixed integer nonlinear programming. So okay, so this is a bus observability index, as I have already explained you in the first slide. Okay, so I think it is clear. And okay, so summary like this, we are using the two-stage branch and bound here, in order to find out the solution. And two-stage branch and bound is based on the depth first search and best first search method. So in stage one, it is just visiting the nodes, not exploring the node. But best first search is exploring the nodes and marking the important nodes for the optimal locations. No, so see, till now, what we have seen here that PMU is very important for the development of smart grid. Okay, and I have shown you that so many things, that is weak buses, PMU, line outage, and partial observability, I have taken into considerations, and even I have taken the these both single PMU outage and single line outage in order to find out the optimal location during these conditions. And I have shown you that BPS, so that is boundary parallelism optimizations, and two-stage branch and bound also I have used in order to find out the minimum and strategic location of phasor measurement unit. And uh, and um, and uh, in the last, I must say that two-stage branch and bound algorithm is always preferable if we are finding the optimal location of PMUs. Okay, and future work. Okay, future work, like, see, there are so many work is going on from last 2 decades, that is based on the uh, solution for optimal PMU placement, and even peoples are working, even scientists are working on micro PMU placement also. And also we can go through the gravitational search algorithm as well as SQP, that is sequential quadratic programming. And also we can hybrid that is PSO and a branch and bound. It means stochastic and deterministic approaches. We can hybrid it so that we can find a better method in order to solve the problem of PMU placement in reasonable time, in polynomial time. And also, like, if we want to measure the efficacy and effectiveness of our method which we have used, so it is better to implement the proposed method in the larger size dimensions of network, that is polish system 2383 and 2736, and so on and so forth. There are around 10,000 bus systems network. And these are the some important points we can take in the future work. And also we can work towards micro PMU placement, because this is the advanced technology for the distribution network. So in this field, there is a lot of opportunity for the researcher, and even distribution state estimation is a new topic, and even many scientists and many engineers, they are working towards it. So these are the references which I have used for making this slide, for making this presentation. And thank you. And I'm happy to take your questions. Please, sir.
So participants, from your end, you can ask anything to Dr. Rohit Babu sir. If you have
And
any
and
doubt,
I'm and I'm
yes,
really
yes, sir.
sorry. Yeah, and I'm really sorry that because of the time constraints, I'm unable to show the codes, because I have planned, but I don't know. Sorry.
Okay,
Yeah.
sir, and no problem, sir. From the participant sides, you may ask if you have any doubt. Please ask Dr. Rohit Babu sir. You can raise your hand and then we'll unmute you. And we have already provided the attendance link in the Zoom chat box, also in YouTube. Okay, so Professor Devarbrata Das sir, over to you to conclude this session. Professor Das sir.
Okay. So, good evening to the Honorable Chief Guest and respected speaker and respected principal sir and all participants and all my colleagues. So, myself, Devabroto Kumar Das from Electrical Engineering Department, Dumka Engineering College. So, I feel honored and privileged to get the opportunity to propose a vote of thanks on this special occasion. So first of all, on behalf of the entire institute, I would like to thank the Techno India Group to provide us such an opportunity to organize a 3-day national seminar. And on behalf of the organizing committee, convey deep regards and heartily thanks to our honorable respected Vice Chairman Sir, Techno India Group Professor Mohit Chatterjee. And heartily thanks to our honorable respected Director of Global Operation, Techno India Group, Mr. Meghdut Roy Choudhury, and Sustainability Director, Techno India Group, Ms. Paul Larabru. And also our beloved honorable respected Sir, Deputy Director, Techno India Group, Dr. Sudipto Chakraborty. So they supported in all possible manner to organize this conference. On behalf of the entire institute, I would like to thank our keynote speaker for day 2, Dr. Rohit Babu. Today, the session is very fruitful for us on the 3-day national level workshop on cutting edge technologies for electrical engineering. So these electrical and electronic technologies are used in all areas of modern society. We nurture students who have indispensable expertise in electrical and electronic engineering, and they go on to become globally successful engineers and research leaders. At our department, cutting-edge research is carried out with a focus on electric power, communication, and electronic and optical devices, integrated circuit and systems, and material properties. So with state-of-the-art research facilities and guidance from teaching staff successful in their respective branches, students can produce and publish research results that they can be proud of. So our sincere thanks to respected Principal Sir of Dumka Engineering College, Professor Ratun Kumar Bose. So thanks, sir, to help us in obtaining the necessary administrative approval for organizing the event. I would like to thank our beloved head of the department, Sir Professor Pankaj Sarkar. Words are not enough to thank their constant guidance and support to save the seminar. And also, I want to express my heartfelt gratitude to Dr. Nirmal Mollik sir, coordinator of such a wonderful session. And I would like to thank the bottom of my heart to all faculties and staffs of Department of Electrical Engineering. Without their help, it is not possible to arrange this event. So finally, my heartiest thanks to all active participants for their presence throughout the sessions. So if time is money, then today you have spent millions for us. Thanks to all of you for making this event successful. And one information, feedback form will be sent to your respective email within a week. So after filling this form, you have to provide an e-certificate. Okay, so over to you, Dr. Nirmal Mullik sir.
Thank you, sir. Dr. Rohit Babu, sir.
Sir.
Yes, sir. From our side, from the Department of Electrical Engineering, Dumka Engineering College, we are presenting you a small memento virtually today, and it will be sent to you offline. Sir, is it visible?
Yeah.
Okay. Thank you for your presence and your valuable presentations in this topic. So tomorrow our session will begin from 3 p.m. and Dr. Abhishek Pal sir, Assistant Professor, Department of E&I, Thapar Institute of Engineering and Technology, Patiala, India. He will provide his views on the topic cutting edge technologies for electrical engineering. So thank you, departmental head, Professor Pankaj Chokas sir, thank you, Deoprata sir, thank you, our resource person, Dr. Rohit Babu sir, and
Thank you, sir. Thank you.
Thank you all the participants.
Thank you, Rohit sir. This is a wonderful session from your
Thank you,
end,
sir.
and I hope this is going to be a very marvelous session for all the participants, those who are present here. So we hope that in future also we will get certain opportunities from you, so that you can lighten the knowledge depth of the students in future also. So thank you very much, sir, from
Thank you.
Electrical Engineering College. Hope in future also you will get such opportunity from you, where we can exhibit more things. Thank you, sir. Thank you very
sir.
much.
Thank you. Thank you, sir. Thank you.
Thank you.
So, sir, shall I leave?
Yes, sir. Yes, sir.
Okay. Thank you, sir. Thank you.